Hello everyone, listening Radio Khanchi 90.4 FM हम सबका रेडियो. I am Dr. Rajeev Asthana, Associate Professor, Gosno College, Ranchi. Today I will discuss quadratic Stark effect in the spectroscopy paper of second semester PG course, Ranchi University. With the exception of hydrogen-like spectra, all atomic spectra show displacements and sometimes splitting in an electric field which are proportional to the square of the electric field strength. Even hydrogen-like spectra show quadratic effect if the field is so weak that its effects are small compared with the fine structure. We use perturbation theory to investigate the quadratic Stark effect. Suppose that a hydrogen-like atom, that is either a hydrogen atom or an alkali metal atom which possesses one valence electron orbiting outside a closed spherically symmetric shell, is subjected to a uniform electric field E applied along z-axis. The Hamiltonian of the system can be split into two parts. First, the unperturbed Hamiltonian, written as H0 is equal to p square upon 2me plus Vr. This is our equation 1. The second one is the perturbed Hamiltonian, written as H1 is equal to E capital E Z. This is equation 2. It is assumed that the unperturbed energy eigenvalues and eigenstates are completely known. The electron spin is irrelevant in this problem because the spin operators all commute with H1, so we can ignore the spin degrees of freedom of the system. This implies that the system possesses no degenerate energy eigenvalues. Actually, this is not true for n not equal to 1 energy levels of H2 atom because of the special properties of a pure Coulomb potential. An energy eigenket of the unperturbed Hamiltonian is characterized by three quantum numbers: the principal quantum number n, the azimuthal quantum number L, and magnetic quantum number m. Let us denote such a ket as NLM and its energy as ENLM. The change in the energy induced by a small external electric field, that is small compared to the typical electric field internal to the atom, is given by the expression delta E NLM is equal to small e modulus of capital E bracket notation NLM Z NLM plus small e square modulus of capital E square summation of modulus of matrix element NLM Z n dash L dash m dash square divided by E NLM minus E n dash L dash m dash. Equation 3. Now as Lz is written as xpy minus ypx, equation 4, therefore commutator of Lzz will be 0, equation 5. Hence, in bracket notation, NLM commutator Lzz n dash L dash m dash equals 0, equation 6. So we will get m minus m dash in bracket multiplied to the matrix element NLM Lzz n dash L dash m dash equals 0. This represents equation 7. Because ket NLM is by definition an eigenstate of Lz corresponding to the eigenvalue mh cross. From equation 7, it is clear that the matrix element is 0 unless m dash is equal to m. This is known as the selection rule for the magnetic quantum number m. Let us now determine the selection rule for azimuthal quantum number L. We have commutator of L square Z is equal to commutator of Lx square Z plus Ly square Z is equal to Lx commutator of Lxz plus commutator Lxz to Lx plus Ly commutator Lyz plus L commutator Lyz Ly, that equals IH cross into within bracket minus LXY minus YLX plus LYX plus XLY equals 2IH cross within bracket LYX minus YLX equals 2IH cross within bracket XLY minus LXY, equation 8. Similarly, commutator of L square Y equals 2IH cross within bracket LXZ minus XLZ, equation 9, and commutator of L square X is equal to 2IH cross within bracket YLZ minus LYZ, equation 10. Now commutator of L square and LZ we have 2H cross square L square Z plus ZL square. On expanding it we will get L to the power 4Z minus 2L square ZL square plus ZL to the power 4 minus 2H cross square within bracket L square Z plus ZL square equals 0. Hence the above equation implies that in bracket notation we have NLM L4Z minus 2L square ZL square plus ZL4 minus 2H cross square L square Z plus ZL square N dash L dash M dash equals 0, as the ket NLM is an eigenstate of L square corresponding to eigenvalue L into L plus 1 H cross square. So the above equation will give, within bracket we have L square into L plus 1 square minus 2L into L plus 1 L dash into L dash plus 1 plus L dash square in bracket L dash plus 1 square minus 2L into L plus 1 minus 2L dash into L dash plus 1 bracket closed, and bracket notation N L M Z N dash L dash M dash equals 0. According to above equation, the matrix element vanishes unless L is equal to L dash is equal to 0 or L dash is equal to L plus minus 1. The matrix element N L M Z N dash L dash M dash in integral form can be written as triple integral psi star N L M function of R dash theta dash phi dash into R dash cos theta dash into psi N dash L dash M dash function of R dash theta dash phi dash. This represents equation 11, where psi N L M X dash equals bracket X dash N L M. However, as the wave function of an L is equal to 0 state is spherically symmetric, that is psi n00 of x dash is equal to psi n00 r dash. Hence the matrix element vanishes by symmetry when L is equal to L dash is equal to 0. So the matrix element is 0 unless L dash is equal to L plus minus 1. This is the selection rule for quantum number L. Now applying the selection rule for M and L to equation 3, we get an expression delta E NLM is equal to small e square into modulus of electric field vector square summation N dash summation L dash is equal to L plus minus 1 of matrix element NLM Z N dash L dash M dash modulus square divided by E NLM minus E N dash L dash M dash. This represents equation 12. We see that all the terms appearing in equation 3 that vary linearly with modulus E vanish by symmetry according to the selection rules. Only those terms that vary quadratically with modulus E survive. Hence, The energy shift given by formula 12 is known as the quadratic Stark effect. In this diagram, it is shown that S2 atom energy levels n is equal to 3 and n is equal to 2 with linear dashed lines and quadratic represented by solid lines, Stark effect represented by horizontal lines, and the corresponding transitions, that is vertical lines, are sigma in solid and pi in dashed lines for electric field value 21.1 volt per meter. The bottom of the figure shows the energy position of the lines and the relative intensities, with the red lines corresponding to the first order Stark effect and the blue lines the second order effect. So here I conclude my lecture on quadratic Stark effect. Thank you very much for listening it.